Have you ever looked up at the night sky and wondered where all those twinkling lights came from? It's a brilliant question. Stars are not just eternal diamonds fixed in the heavens. They are born. They live for billions of years and then they die. Just like us, every star has a life story. It is a story written in fire and light across vast stretches of space and time. This epic journey begins in the quietest, coldest and darkest corners of our universe. It all starts inside enormous, beautiful clouds of gas and dust that drift between the galaxies. These cosmic nurseries are where the magic of star birth begins to unfold, slowly, patiently, over millions of years. These immense clouds are called nebulae. Imagine them as giant, colorful, cosmic wombs. Inside these clouds, tiny particles of dust and gas float around, but they are not alone. Gravity, the same force that keeps your feet on the ground, is at work here too. It gently pulls these particles together. Over a very, very long time, clumps begin to form. As more and more material gathers, the clump grows bigger and bigger. Its gravity becomes stronger, pulling in even more gas and dust. It's like a snowball rolling down a hill, except this snowball is destined to become a star, a furnace of unimaginable power. As the clump of gas and dust collapses, the pressure at its center builds up. It gets hotter and hotter, squeezed by its own immense weight. This hot, dense core is called a protostar. It's not quite a star yet, but it's getting there. It glows with a dull red light from the heat of its own compression. For this infant star, it is a critical time. It continues to pull in more material from the surrounding nebula, growing in mass and temperature. This phase can last for hundreds of thousands of years, a mere moment in the life of a star, but a crucial step on its journey to igniting into a brilliant beacon of light. Finally, the moment arrives. The core of the protostar becomes so incredibly hot and dense, millions of degrees Celsius, that something amazing happens. A process called nuclear fusion begins. Tiny atoms of hydrogen, the most common element in the universe, are forced together to create helium. This reaction releases a tremendous amount of energy. This energy pushes outwards, perfectly balancing the inward pull of gravity. The star ignites. It is now a stable, shining star, entering the longest and most peaceful phase of its life. We call this a main sequence star. Our own sun is a main sequence star, and it has been shining steadily for nearly 5 billion years. Once a star joins the main sequence, its future is already decided. The single most important factor that determines its entire life story is its mass. How much stuff did it manage to gather during its birth? This is the great divide in the stellar world. Stars come in all sorts of sizes. Some are small and cool, known as red dwarfs. They sip their hydrogen fuel very slowly and can live for trillions of years, far longer than the current age of the universe. Others are medium-sized, like our sun. And then there are the giants, massive stars that are dozens of times heavier than our sun. These giants live fast and die young. Let's look at stars like our sun first. These are the average common stars of the cosmos. For about 10 billion years, our sun will happily fuse hydrogen into helium in its core. But no fuel lasts forever. Eventually, the hydrogen in the core will run out. When this happens, the delicate balance between gravity and energy is broken. Gravity will start to win, squeezing the core even tighter. This will make the core even hotter. The outer layers of the star will then expand outwards, cool down, and glow with a reddish light. The star will swell up into a magnificent but temporary state, a red giant. When our sun becomes a red giant, it will be enormous. It will swell so much that it will engulf the orbits of Mercury, Venus, and possibly even Earth. It will be a completely different star from the one we know today. After this dramatic expansion, the star's life enters its final chapter. The outer layers of the red giant will drift away into space, forming a beautiful glowing shell of gas called a planetary nebula. It looks a bit like a planet through early telescopes, which is how it got its name, but it has nothing to do with planets. It's the ghost of a dying star, returning its material to the cosmos. What's left behind at the center of the planetary nebula is the star's hot, dense core. This remnant is called a white dwarf. It is incredibly dense. A teaspoon of its material would weigh as much as a car. A white dwarf no longer produces new energy through fusion. It is like a glowing ember, slowly cooling down over billions and billions of years. It will eventually fade into a cold, dark object known as a black dwarf, a dead star drifting silently through the darkness. This is the calm, quiet end awaiting stars like our sun. It is a peaceful retirement after a long and brilliant life. The story is very different for the most massive stars in the universe. These are the cosmic heavyweights, more than 8 times the mass of our Sun. Because they are so massive, their gravity is incredibly strong. This means the pressure in their cores is immense, causing them to burn through their hydrogen fuel at a furious rate. While our Sun will live for 10 billion years, these giants live for only a few million years. They live fast, shine incredibly brightly, and die in the most spectacular way imaginable. Their end is not a quiet fade into darkness, it is a violent universe-shaking explosion. Just like a sun-like star, a massive star runs out of hydrogen in its core. It too swells up, but it becomes something even bigger than a red giant. It becomes a red supergiant. Betelgeuse, the bright red star in the constellation of Orion, is a famous example. Inside the core of a supergiant, fusion doesn't stop with helium. The immense pressure allows it to fuse heavier and heavier elements. Helium into carbon, carbon into neon, and so on, all the way up to iron. The star's core becomes like an onion, with layers of different elements, with the heaviest, iron, at the very center. But creating iron is where the trouble begins. Fusing elements up to iron releases energy, which helps the star fight against gravity. But fusing iron actually takes energy away. So when the core fills with iron, the star's energy source is suddenly switched off. Without the outward push from fusion, gravity wins instantly and catastrophically. In less than a second, the core collapses under its own tremendous weight. The outer layers of the star come crashing down onto the core and then rebound in a titanic explosion. This is a supernova. For a few weeks, a single supernova can outshine an entire galaxy of billions of stars. This explosion is one of the most important events in the cosmos. It blasts all those heavy elements the star created, carbon, oxygen, iron, far out into space. In fact, the energy of the supernova itself is so immense that it forges even heavier elements like gold, silver, and platinum. Every atom of gold on your finger was created in the heart of a supernova explosion billions of years ago. The very iron in your blood was forged inside a massive star that lived and died long before our Sun was even born. We are, in a very real sense, made of stardust. After the sound and fury of a supernova, what is left behind? The answer once again depends on mass. If the original star was big but not too big, the collapsed core survives as an object called a neutron star. This is one of the strangest and most extreme objects in the universe. It is a city-sized ball of neutrons, so dense that a single sugar cube-sized piece would weigh more than all of humanity combined. Some neutron stars spin incredibly fast, hundreds of times per second. As they spin, they sweep beams of radiation across space, like a cosmic lighthouse. If one of these beams happens to point towards Earth, we see it as a regular pulse of light. We call these objects pulsars. Sometimes a neutron star is born with an unbelievably powerful magnetic field, 1,000 trillion times stronger than Earth's. These are called magnetars. Their magnetic fields are so strong they can warp atoms and cause starquakes on their surface, releasing huge bursts of high-energy gamma rays. But if the original star was truly massive, more than 20 times the mass of our Sun, then nothing can stop its collapse. Gravity crushes the core completely, squeezing it down to an infinitely small point with infinite density. It creates a black hole, an object with gravity so powerful that nothing, not even light, can escape its grasp. These stellar remnants, white dwarfs, neutron stars, and black holes are not just cosmic curiosities. They are clues that help us understand the history of the universe. By studying them, we can learn about the lives of stars that died long ago. And the material blasted out by supernova becomes the raw material for the next generation. The clouds of gas and dust are enriched with heavy elements, providing the building blocks for new stars, new planets, and perhaps new life. The death of one star is the beginning of another. It is a grand cosmic cycle of death and rebirth. With powerful new instruments like the James Webb Space Telescope, we are peering deeper into this cycle than ever before. We can see right into the dusty hearts of nebulae where new stars are being born. We can study the atmospheres of distant planets and analyze the beautiful expanding shells of dying stars in stunning detail. Each new image, each new piece of data helps us piece together the story of the cosmos. Understanding the life and death of stars is fundamental. It tells us where we came from, what the universe is made of, and how our own small world fits into this vast, magnificent, and ever-changing cosmic drama.